Yes, okay. I'm very happy that I was told in no uncertain terms that it's okay if this talk is very short, because in fact, what I'm going to show you is quite trivial. But maybe, oh, I have to admit, Pritam, okay. But maybe you'll think of something less trivial to do with it. So this is joint work with my good friend Stephan Mertens, and so I'm going to be talking about percolation, for instance, on the square lattice. So here is a 5x5 grid, and some of these sites, the gray ones are occupied and the others are empty, and the gray ones have a path from the top edge to the bottom edge. So I will call a subset of sites like this one a spanning configuration, specifically with a path from the top to the bottom. Of course, you can consider various other sorts of spanning and crossing configurations. Now, physicists like to do numerical experiments, and among other things, to try to estimate numerically the critical density of sites at which there is typically, with high probability, a path from top to bottom in the limit of large lattice sizes. And so one way to do these experiments is Monte Carlo experiments on large lattices, but another one is to do explicit exact enumeration on somewhat small lattices. So here, for instance, is a, here, for instance, is an exact enumeration of spanning configurations on an 8x8 lattice. And so A sub n comma m of k will be the number of configurations on an n by m lattice with k occupied sites. The red curve here is the set of all configurations. That's just 64 choose k. And then the blue curve is the number of spanning configurations. And so you can see that somewhere where k is a bit more than half of 64, the ratio between these two is close to 1, indicating that we've crossed that percolation threshold. And so one thing you can do with this series is form a generating function where we weight the number of spanning configurations with k occupied sites by z to the k, and then vary z. And for instance, one thing you could do with that is calculate exactly on a given lattice the probability that a configuration is crossing if each site is independently occupied with probability p. And so that, for instance, gives us curves like this. So these are these exact calculations of this crossing probability as a function of p on a 5x5, 11x11, and 22x22 lattice. And you can see that already, even though these lattices are quite small by the standards of numerical experiments in physics, they're already starting to intersect quite close to the critical point, the critical density, which we believe the first 6 digits of are these. And so, yeah, it turns out that this kind of exact enumeration and then various kinds of extrapolation of these intersections of these polynomials seem to give a very good estimates of the critical density, and in fact, kind of the leading estimates with the most significant digits that physicists are confident in come from this method at the moment. Okay, so if you're going to do this experiment, you can kind of play around with this generating function. And one thing that Stephan did was he substituted in -1. And then, of course, this generating function is just the number of configurations with an even number of occupied sites minus the number with an odd number of occupied sites. And he noticed a surprising pattern, which was that these differences were all +1 or -1. So the number of spanning configurations with an even or odd number of sites seems to differ by + or -1. And in particular, that also means that the total number of spanning configurations on the square lattice is always odd. So of course, when he noticed this, he started looking around for some sort of explanation. And you already know what kind of explanation you want to look for. It would be a matching proof, a pairing proof, if we could give each spanning configuration a partner with the opposite parity, then these would line up, and maybe there's one left over and whether that one spanning configuration which is unpartnered is even or odd would determine the sign of that difference before. Okay, so you've probably seen this kind of proof before, and that's the kind of proof which we looked for. Now, the proof I'm going to show you is, I mean, I think there's only like 3 minutes left in this talk. It's going to be very simple. In my defense or in my attack, it took us a week of really hard work to find it. But once we found it, it's fairly simple. So here's what we're going to do. And, clearly the nicest way to switch the parity would be to find a single site in the lattice, which we can turn on or off, which we can flip. And we have to be a little bit careful because whatever the rule is for flipping that site, in order for this to be a matching, the same rule then has to tell us to flip that same site back. So we struggled a lot with, find the leftmost path and the lexicographically first path, and then flip some other site that isn't on that path. And we kept finding annoying cases where a rule didn't work, and we drank a lot of wine and so on. So eventually we found the following procedure. So start by looking at row number 2 from the top and look for the leftmost unoccupied site in that row, which is this one. Now flip the site in row 1 above that unoccupied site, which is that one. Well, notice that this is not going to disturb any path which goes from top to bottom through the lattice. That path has to get to row 2 somehow. It has to get there through row 1. And because this is the square lattice with just north-southeast connections, flipping that site, which I have there in black, can neither create nor destroy such a path. And our prescription for which site to flip is the one above the leftmost unoccupied site in row 2. Well, that site is still unoccupied because we didn't flip that one. And so the matching will tell us to flip that back. Okay, so this produces partners for a bunch of configurations, but not for those where row 2 is completely full. So then let's look at row number 4, the next even numbered row. Look at its leftmost unoccupied site and flip the one above that, and the same argument applies. This is not going to disturb any path which gets down to row 4. That, of course, will not work if row 4 is completely full. So anyway, if all the even numbered rows are completely full, you have to do something else. On the other hand, if all the even numbered rows are completely full, we know what the spanning configurations are like. They're simply those where every odd numbered row has at least one occupied site, because then it's very easy to get all the way from the top to the bottom. Now we could already then just write down using the binomial formula the parity of those, but let's push this partnering thing a little bit farther. So here is such a configuration. The even numbered rows are full. Well, simply flip the leftmost site on row number 1. Obviously, that doesn't change the fact that the top row has at least one occupied site, unless the leftmost one was the only occupied site. Oh, well, in that case, look at row number 3 and flip the leftmost site there. Okay, so great. There's one configuration left over for which we haven't defined a partner, and it's this one. It's the one where all the even numbered rows are completely full, and all the odd numbered rows, the only occupied site is the leftmost one. And so flipping that would destroy the fact that we have a path from top to bottom. So this is our one configuration left over. How many occupied sites does it have? Well, there are m/2 rounded down even numbered rows, and each of them has width n. Sorry, m here is the number of rows and n is the number of columns. And there are m/2 rounded up odd numbered rows, and so that's the total number of occupied sites. And if you raise -1 to that, you find that indeed it matches Stephan's numerical results. And so, yeah, so now you can all go have lunch. So you may have noticed that this very same proof applies to lots of other lattices, right? So for instance, it applies to so-called cylindrical boundary conditions, where we have, you know, circles like this, because just replace, every time I said leftmost, just replace it with first in some ordering, going around that lattice. It also works for cubic lattices. Hey, look, cubic lattices in any dimension, hypercubic lattices. Indeed, it works for any product, I guess you would call this a weak graph product, of a path from top to bottom with any graph. Okay, so there you go. It does not, in fact, work for, say, the triangular lattice, which is too bad. If you calculate the same difference between configurations with odd and even numbers of occupied sites, you don't get plus or minus 1. You get something that looks more like it's growing sort of with the square root of the size or whatever you would expect. So we don't have a similar result on triangular lattices. And the reason there is that we don't just have these, if you will, vertical bonds from one copy of the layer to the other. Oh, this is terrible. Someone's joining the talk and I'm almost done. So, well,
Sorry,
I was
Cris,
promised that a short talk was acceptable. So except for another slide of discussion.
So Cris, I have a question.
Yes, please.
Yeah, so I still don't really see why the argument doesn't work for triangular lattice. Like, it still have this even odd distinction, and it also still have it's still planar. So what is the thing that fails here?
Right, it's certainly still planar, although I guess the example of these higher dimensional lattices shows that planarity isn't really the issue. I think the issue is that the layers are identical and one layer is connected to the next layer just by these parallel vertical bonds. So I don't know if you can see my mouse on the screen. Can you see my mouse? Some of you can, some of you can't. So if you think about the triangular lattice, suppose that the leftmost site on row number 2 is unoccupied. So, well, actually, suppose that the middle site on row number 2 was unoccupied. And then we flipped one of the sites above it on row number 1. Well, it has 2 bonds leading up to row number 1. So we would have 2 different choices of which one to flip. But suppose the only spanning path came through, for instance, the middle site on row number 1, and then went down to the leftmost site on row number 2, and then continued. Well, then flipping that one could destroy that path, and that would match a spanning configuration with a non-spanning configuration. Yeah, good. Okay. Well, so, you know, what is there left to say? As you know, this kind of trick of defining an involution or a partial involution between things and then seeing what's left over that doesn't have a partner is handy in several ways. One of them is Peter Winkler's lovely puzzle. I forget whether it was light switches or a row of lockers in a high school or something, but you know, somebody comes through, and let's say it's light switches. Okay, there are n light switches. Actually, there's an infinite number of light switches. Somebody comes through and they all the light switches start off by being off. Somebody comes through and they flip every single one in turn. Then the next person comes through and they flip the second one, the fourth one, the sixth one, all the even numbered ones. And the next person comes through and flips all the ones labeled by a multiple of 3, and so on. And this continues, if you like, forever, or until the thing we're a multiple of exceeds the number of light switches. Which light switches are on and which ones are off? Well, this is the parity. Maybe I should let you think about this puzzle since we have plenty of time. But anyway, it has to do with the parity of the number of divisors that a given thing has, right? Because the number of times it got flipped is the number of divisors it has. And you can come up with a nice involution-based proof that square integers have odd numbers of divisors and non-square integers have even numbers of divisors. Okay. Igor reminded me in the emails leading up to this that The number of binary trees with a certain number of leaves, aka the Catalan number, is odd if the number of leaves in the tree is 2 to the n, and even otherwise. And these are, trees where every internal node has either, every node has either 0, 1, or 2 children. And then finally, there's the classic proof, due to who's he what? I can't remember, don't have it here. The classic involution-based proof that primes of the form 4n plus 1 have an odd number of representations as the sum of 2 squares, and in particular have at least one such representation. So I think it's very sweet. I'm on an email list that was discussing recently examples of things where we show that something exists because the number of them is odd, which I think is a great way to show that at least one such thing exists. Okay, well, that's really all I wanted to say. Buy my book, but I'm not going anywhere if you want to discuss.
So I am.